So one type of problem that we can solve with integrals, and therefore we can use the fundamental theorem of calculus to get an answer to, is integration of a rate of change. You already know about an example of this. I'll put that up in a minute. But you know about the example of how if you integrate velocity, which is a rate of change, you get the position or displacement of a function, sorry, of an object. Let me just state the general principle. So let's suppose that f of t gives the rate at which some quantity is changing at time t. So it's not the total amount of the quantity that you have, it's the rate at which the total quantity is changing. In that case, if we integrate the function f of t from a to b, in other words, where a and b are times, because the variable here is t for time, then what we get is the total amount that that thing changed between time a and time b. Here's the example that you already know. We know about velocity, so let's state very precisely what we know about the relationship between velocity and position using integrals. We know that if velocity, we think of it as a sort of a speed, assigned speed. It's a speed with a direction, but more precisely, it's understood as the rate at which the displacement or position of the object is changing. That's how we started it when back in one of the earlier chapters. We were given a position function called s of t and said its derivative is the velocity. So that means the velocity is simply the rate at which the position function is changing. If instead we're given a velocity function, we're told how fast and what direction an object is moving at time t, we can use that to answer the question of how much did the object change its position, change its net position between time a and time b. So, for example, if I have an object that is if I have an object that's moving, there's v and there's t. So let's suppose that I have an object that it's moving, it's accelerating, it's going from a speed of 0 up to a speed of 2, and then it goes back down to a speed of 0. We can see that between time a and time b, the object actually moved an amount that's equal to this area. Even though the object got back to speed 0, it was always moving at a positive velocity. So this is going to be a total positive amount of area because the object certainly moved a positive amount away from its initial position, even as it sped up to 2 and then sped back, then slowed back down to 0. So the way that you can think of this, however, you can think of this as kind of like a multiplication problem. If I write the integral from a to b of v of t dt, think about the units that this is being measured in. Velocity is probably going to be measured in some units like meters per second or miles per hour, kilometers per hour. It doesn't matter. The point is it's going to be some amount of distance per unit of time. So if distance is measured in meters and time is measured in seconds, then velocity is measured in meters per second. And this is dt, which is going to be a quantity of time. Yes, it's a very little tiny quantity of time, but it's still on the time axis, so it's still time, and that's measured in seconds. If you multiply these two things together, meters per second times seconds, then using that thing that chemistry teachers inexplicably call dimensional analysis, you multiply these units together and you get meters. That's correct. In other words, if you think about it, you're taking meters per second, multiplying it by seconds, and you're getting meters, which is exactly what you want. Our claim is that this is the total distance, so it should be measured in meters. Oops, sorry, it's a little bit sloppy there. Total distance. Okay. And this is sort of a clue that you've set up the problem correctly and that you understand what it is that you're measuring. If you look at the function and ask what is it being measured in, and then you look at the differential and ask what is that being measured in. So if you're trying to get an answer in meters, and you've got meters per second times seconds, then there's a good chance that you've got the setup correctly. So I've put up this problem just to take this a little bit out of the realm of velocity and distance, just to give you a different context for this. So the problem is water is flowing into a tank at a rate of f of t equals t squared plus 1 over t squared gallons per minute at time t. So in other words, what that means is that at time, let's say 5 seconds, we can conclude that the rate that the water is flowing into the tank at a rate of 5 squared, which is 25, plus 1 over 25, in other words, whatever that number comes out to, 25 and 1/25 gallons per minute. That's the rate at time 5 minutes that the water is flowing into the tank. So the question is how much water flowed into the tank between t equals 1 and t equals 4. This is, of course, one of the remarkable facts about calculus, is that we can use a rate of change to answer a total accumulation problem like this. So what we want to do is we want to set this up in the following way. The total water, and I don't want to say it's total water in the tank. It's the total amount of water that flows into the tank between these times. So I just don't want to rewrite what's already in the problem. So the total amount of water that flows in between t equals 1 and t equals 4 is going to be integral from 1 to 4 of f of t dt. And we can pretty much guess that we've got the integral set up right because f of t is measured in gallons per minute. It's minutes. And d of t is measured in minutes. So when I multiply them together, I get gallons. And that's the quantity I want. If I'm asking how much water flowed in between two times, I'm not going to answer it in gallons per minute. You're going to answer it in gallons. If I ask you if you want a drink of water, and and you say, and ask how much water you would like, you're not going to say, well, I'd like 5 ounces of water per second. You're going to tell me, get me an 8-ounce glass of water. In other words, you're going to measure it in a unit of volume, not a unit of volume per minute. So anyway, so this is what's giving this is what's giving the total amount of water between t equals 1 and t equals 4 is going to be this integral. We can fill in the blanks here and write this up as integral from 1 to 4 of the function is t squared plus 1 over t squared dt. We're going to find an antiderivative, so that's going to be t cubed over 3, and then this will be minus 1 over t, and we're going to let that go from 1 to 4. So this is now going to be, let's see, 64 over 3 minus 1 over 4 minus 1 over 3 minus 1 over 1. We simplify that, we get 63 over 3, and this comes out to negative 1/4 plus, this is a double negative, minus negative 1 over 1. Adding that to the 1/4, I get 3/4. So 63 over 3 is 21, so that's 21 and 3/4. So what's the physical interpretation of this? It means that if I check the volume, if I check the amount of water in the tank at time 1 and then come back and check it later at time 4, I will find that there's 21 and 3/4 gallons more water in the tank than there had been at time 1.